All right. Hey, everybody. My name is Patrick, and I'm here today to talk about an interesting project that we had a lot of fun with. This is a bounty for the Gitcoin project, and it's implementing an optimal algorithm for parallel swap as implemented on the Near protocol using the Ref Finance contract project. And so just to begin with, I want to give a quick overview of the problem statement. And so in many liquidity pools, in some of the traditional ones that were first started like Uniswap or PancakeSwap, there are typically only a single liquidity pool for each pair of tokens. And so let's say we wanted to go from token A to token B. There would typically only be one pool that you can have people put liquidity into and then do swaps between it. Using the constant product bonding curve, so the xy equals a constant formula. And so the interesting thing that they introduced in Ref Finance was the ability to have multiple liquidity pools, each for the token pair between A and B. And so because each of these pools is different and they can typically have different amounts of reserves of each token, so pool 1 could have, say, A1 amount of token A, B1 amount of token B, and then this gamma 1 as its fee. You could have the different amounts for each of these different pools just depending how they were set up and what's been swapped into and out of them. And so the interesting thing is, how can you trade token A in such that you allocate a certain amount of that token A to each of these pools, that you get the maximum amount of token B out. So that's the basic problem, is trying to maximize the amount of token B we get out if you split in a single transaction across these multiple pools and go in parallel. And so we got to do some fun math in order to figure out how to do this. And cranking through it, we were able to find the initial math is a little bit difficult, but once you get through it, there's a really elegant, just very simple solution and simple closed form solution for finding this, how much you allocate to each pool. But we found that it is actually a function of the amount that's in each pool and the fees. And so it's not just the same percentage that's allocated to each pool, no matter how much of token A you want to trade in. So it's actually a function of that. And so I thought that was kind of interesting. So anyway, the technique that we use has to do with Lagrange multipliers, and if you're interested in learning more about that, we did write a white paper to go into a little more technical detail on how we did that, and the link to that will be in the GitHub repo. As always, if you guys have any questions about any of this, about Web3, about automated market makers, or any of this, or any of our white paper or any of the projects we've done, please reach out to us, whether on our GitHub page or elsewhere. We'd always be happy to talk. All right, and so that's the problem statement as it is. And so probably the more interesting piece will be showing the front end of how we actually implement this and interact with the Near protocol and the Ref Finance contract. Before I do that, real quick, I'll just say, here's just a visual picture of the algorithm that we used. And so you have a certain amount of liquidity pools and then a certain amount total of token A you want to trade in. First, you have to calculate this quantity called mu that's just a function of these pools and the amount you want to trade in. This will give you a way of calculating the delta A sub I for each of the pools. So this is the part of the total delta A that you want to give to each of the pools. And so one of the important steps is checking to see if any of these delta A's are less than 0, so if any of them are negative. If that's the case, then you have to set that component to 0, because we assume you can't trade in a negative number. And again, the math in the white paper goes a little more into why this is. And then we remove that pool from the list, and then recalculate with the new set of pools a new value of mu, and then reallocate all these delta A sub i's. And then eventually at the end, you end up with delta A sub I for each of the pools. Okay, and so that's probably enough of talking about that. let me go ahead and jump onto the front end for this. And so if you download and clone the Git repo, and then bring a command window or Visual Studio Code or something, and then say make sure you have Node.js installed on your computer, and then you can say npm run dev, and this will set up a local server. So let's see, here's the newest one that popped up. And so you can see here, this is just the near parallel swap. So it's a basic front end. I was able to use this template, and the link to it's in the GitHub page. But the initial template that I'm using and have added onto, I didn't originally create, but I appreciate the person who did. So, and so if we go on here and look at, you can choose your input token and your output token, the amount that you want to swap in, and then you calculate the best swaps to get the total amount of this token to out. And so if I go ahead and scroll down here a little bit, you'll notice that it's actually already interacted with the Ref Finance contract and the Near protocol. And so here it's grabbed all of the liquidity pools, and this is the reffinance.testnet. And so that can be configured in the code, that can be updated. But you'll notice there are a lot of different tokens on here. And so if we go up here, we can just pick, say, a random one. Let's try maybe banana. And if you want to trade it for the wrapped testnet token, and then put in just, I don't know, some large amount here, and then hit calculate best swap. You'll see you get large amount out. That's a really huge number, but I assume that's just because of the conversion rate between the value of banana versus wrap testnet. And you'll notice here that all of the other pools have disappeared. There was actually another wrap testnet going to banana, but it had 0 liquidity in it, and so because of that it got dropped off. And so you'll notice here, so this is the amount we wanted to swap in. Now if we decrease this sum and recalculate, get a different number output here, although the allocation percentage is still the same, and so I can keep decreasing it. And what you'll notice is something kind of interesting. If I keep decreasing it enough, the percentage allocation is going up for the bottom pool, and it's going down for the top pool. And so I can do it down again, and now suddenly when it's down to this amount, all of it should be allocated to pool 15. So I can try and add another number here to just see, and that sort of splits it a little bit. Just trying to see if I can converge it down to close to 50% each. So anyway, you could mess with it and see. But I think the interesting thing that's probably going on here is this pool 15 probably has a slightly better price than pool 11, just based on the ratio of the reserves. But at the same time, pool 11 probably has a much higher liquidity, and so once you trade a little bit into pool 15, it probably induces a certain amount of slippage, and then once you have a large enough amount of slippage, if you try and trade in any more, it's more advantageous to go to pool 11. And so the cool thing is that our closed form solution takes all of that into account, and it'll calculate that for you. And so you can also swap these. So we could go, say that was banana to wrap, but if we wanted to go from wrap testnet back to banana, probably gonna have to put a much larger number in. So we just add a bunch of 9s, calculate. All right, so in this case, it's saying go do everything from that pool. I can do it down again and see if we get any of the same results. Probably not, but just based on the inversion. So anyway, that shows how that works. You can also jump to, say, some other set of tokens. Here's a going from token 1.reffinance to token 2. I'll say calculate best swaps. And you'll notice down here, this changed the pools that are here now, and so now that's pools 0 through 3. And it looks like really only the first one has the most liquidity in it probably and has the best price, and there's, you know, a teeny amount being allocated to some of the other ones, but those probably have very little liquidity. And then this is the amount you would expect out. So the cool thing about this that I should also mention is that the total amount that we're calculating to come out, we've compared with the with actually querying the contract to see there's a get return function on the refinance contract, and we get consistent results with that. But ideally you wouldn't want to query that ahead of time, and so in order to have low complicity, we don't want to broadcast what we're trying to do before, so we don't get front run if you're trying to submit all of these transactions in parallel. So really the only transaction we have to query is to query for all the pools and to get all of their different quantities of reserves of tokens, and then from that you can immediately run the optimization function for a given amount that you want to trade in, and it'll give you the estimated amount out. So all of this is being calculated off chain. The only thing that's going on chain is the initial grabbing these different pools and testing that. And so that is about it. So that's the front end, that's the algorithm. Again, we have a white paper that you can link to in the GitHub page. And if you have any other questions, we're more than happy to talk with you. Please reach out on GitHub. And thank you so much for your time. Have a good day.